Okay, welcome back. So the idea of today is we want to describe or discuss compact subspaces of Euclidean spaces, or to the end. So to begin with, last time we proved that any closed interval AB inside of the real line is compact. But we didn't get to discuss applications. So what I want to start this lecture with is something you know from analysis. So this you should know from previous classes, the extreme value theorem. So this theorem is about continuous functions going out of a closed interval, a bit close and bound to the reals. So if you have a continuous map like this, then the theorem says that it will attain maximum and minimum values. So there exists some x min and some x max in our closed interval, the domain, such that for any x that you have in your interval, the function is going to take x to most whatever it does with x max, and at least what it does with x min. So what we're saying here is, if you have a function going out of a closed bounded interval, then you can be sure you will obtain maximum and minimum values within that interval. And now what we want to do today, to begin with, is prove a generalized version of this. So general version will look like the following. Let's call this again, maybe the extreme value theorem. It's going to be pretty much the same theorem as before, but instead of AB, I will just take any compact space. So I will copy this. I will copy this and just change, just change AB for a compact space. So if you have a continuous map, and now I need to change AB for a continuous space, for a compact space. So it's continuous, where the domain is compact. Then exact same statement. They're going to exist x min and x max in the compact domain, such that the function will take any element in the domain into that interval. So let me maybe move this over here. So we want to prove this theorem. And the idea will be, as a preliminary results, let's prove this lemma. So I want to prove that if we have something we never proved before, but I mentioned this, if you have a subspace of R, which is compact, then this subspace is going to contain its maximum. So there exists some, let's call this M value in Y, such that any other element is going to be at most M. And that's for any Y in capital Y. So for the proof of these results, so what we're saying in other words is, we're first saying our M will look like this. So this is the real line. Our Y is a compact subspace. Don't really know what it looks like. So we're saying two things. First, that Y is bounded, and that the maximum, the supremum, actually is a maximum. So it lives in Y. This is what we're saying. So to prove this, let me change the template because it's good. So to prove these results, let's assume this is not true. So assume for a contradiction that this is not true. So we're claiming no such M here can exist. So no such M exists. If that happens, then for every M in Y, we know that this is not possible, right? So there must exist some little y in the set such that, well, y is bigger than M. So we're saying is if you take any element in Y, you are always going to have that element inside one of these intervals, negative infinite. So sorry, I don't know what happened. So what we're saying is any element in Y will be an element in that one of these sets. In other words, the set Y is going to be included in this union. The Y ranges over any element in Y. And now we can use that Y is compact. So these guys, all of them are open in R. So since Y is compact, we don't need all of them to cover Y. We only need finitely many. So we know there exists finite amount of Y's. Let's call them Y1, blah, 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 Y n in Y elements such that our set Y is actually going to be inside the union of finitely many of these intervals. Okay, so what's good about this union is just going to be one of these intervals. If we take the maximum Y, so if we take the maximum one, let's call that Y star. Y1 through Ym. We have that our Y is inside negative infinite Y star. But the thing is, this maximum over here is the maximum of things in Y, finitely many. So this Y star, which is the maximum of things in Y, is actually going to be one of these Y's. So it is an element in our set Y. So the problem with this is that Y star supposedly lives in the set Y and not in the interval. Because, yeah, it's not smaller than Y star. And this is the contradiction that we wanted to get. So this proves indirectly, when we go up to our statement, this proves indirectly that this M over here, this M needs to exist. Okay, so that's our lemma. So second result or second proof is just the extreme value theorem. So proof of the extreme value theorem. Just going to uh, uh, use the previous result. So remember, we have a continuous function f going from x to r. This is a continuous function. And we also know that x is compact. That's what we're assuming. In this case, we proved in class, we proved that the image of x, which is a subset of R, is also compact. And the thing is, I want to take this guy as my y in the previous lemma, as my set y, which is compact, subspace of R. So in this case, by the lemma that we just proved, lemma 1, we know there exists some y star, let's call this, in f of x, such that maybe let's stick with the previous notation. Let's call this guy m, such that y is more than or equal to m for every y in f of x. And now we just need to translate these two guys. So since our m lives in f of x, we actually have that m looks like f of x max for some x max, because it lives in the image for some x max in our set x. So now for any x in the compact space X, we know that f of little x will live in f of big X. And just by translating this, I can take this guy as little y now. What we have is that f of x is going to be smaller than or equal to f of x max, which is f. So I'm just translating this inequality here to elements in x. So this is how you prove the existence of x max and existence of x min follows similarly. And for this, you kind of know it at a lower version of lemma 1. So let me just say this and finish the proof here. Okay, that's how we prove the extreme value theorem. So let me go up to our first slide. If you were wondering when you study analysis, what was the important thing about these results? In analysis, well, the answer is you only need your. So why do you take here AB instead of any open interval, for example? Well, because you need it to be compact for this theorem to be true. This is what's behind everything. Okay, so now let's actually describe or discuss compactness in higher Euclidean spaces. So I'll start this discussion with a definition. I will kind of give two definitions of this concept. The first one that's particular to our n, so a subset, let's call this x instead of our n, is said to be bounded. If you can insert it into an open ball. or some, well, not necessarily open. So if there exists some radius, positive real number, such that the norm of any x will be at most this radius, and that's for any x, big X. So in other words, we're saying here, so maybe let's just stick with smaller, strictly smaller. In words, X is a subset of this equivalent ball. If you learn smaller or equal, you need to take the closure of the ball. But this is more clear. Okay, so this is what I'm defining here. What's a bounded subset of Rn? Now, I'm sorry, why do we care about this? Because we can describe compact spaces with this notion. So theorem 2. Subspace of the Euclidean space Rn is compact if and only if it is closed and bounded. So kind of joking, I said some time ago that a compact subspace or a compact space is something that you can like hack and feel like you're hacking it. So this is when we really bounded and we close it. So bounded will mean you can hack it, and closed mean you can feel the boundary. So proof. Why is this true? So let's maybe go with this direction first. So let's assume we have a compact subspace. I want to show it's closed and bounded. So proving that it's closed, it's not going to be that complicated because we have some previous results, namely the ambient space is a metric space, and any metric space is always Hausdorff. And we proved, let me fetch the theorem here. So since Rn is Hausdorff, we know from proposition 4 of lecture 12, or 20, sorry. So prop 20.4, that's our, that any compact subspace of a Hausdorff space is closed. So X is closed in Rn. Any compact subspace of a Hausdorff space is closed. So that's easy. That was already proven. Now we also need to show it's bounded. And to show it's bounded, to show X is bounded, we'll just go by definition here and construct an open cover. Let's just use open balls. X is inside R to the n, which is the union over all possible radii. So over any positive real of these balls. So since we have this open cover and X is compact, probably I could emphasize these guys are open. Since we have these, we actually have we actually have X inside union of finite to many of these. So B0 R1 union blah 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 B0 Rm RK for some radii, for some R1, blah, 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 blah. Okay. But the thing is, these balls, you take the union, you're just going to grab the biggest one. So if we take biggest radius, R to be the max of this radii, or one. So okay, we get that X is actually inside that open ball, which means that X is bounded. That's what we want to prove. So we just prove if X is compact, then it's closed and bounded. And here we assume X is closed and bounded and prove it's compact. So essentially what I want to do is I wanted to use this proposition. If you have a closed space in a compact space, then you are compact. But the thing is, X is closed in Rn, not necessarily closed in a compact space, because R to the n is not compact. So what I'm trying to do first is use these to show that X is actually inside the compact space. That's how we start this proof. So since X is bounded, what you actually have is X is inside some open. So we don't know what the radius is, but that's not important. We know it's inside some open. And the idea now is this open ball is always going to be inside this kind of square or cube if you're in dimensions 2 or 3. So inside this negative r to the n. Right? By this, I mean the Cartesian product n times of this guy. So what we have is that X is inside this guy here. But this guy, so each of these intervals, this is compact inside of R. That's what we proved last time. Now we're taking the finite product of those. So this guy is compact. So I can say, since X is closed in the compact space, negative R to R n times, we proved in proposition, so we know from prop, this will be prop 20.3, that X itself is compact. And that's what we want to prove. So that's the end of this. So most of the work was already done before. We just wanted to use these guys compact and then propositions 20.3 and 20.4. Okay, so I will just once again emphasize we kind of understand what's a compact subspace of Rn. It's closed and bounded. So this was our theorem too. And now we'll change a little bit of topic. So you might want to pause the video for a second now, and then you can come back like in 10 or 13, in 10 or 15 minutes. Want to discuss now compact metric spaces. So it's still very related. So let me start with the definition. We already defined what's a bounded subspace or subset of Rn, but I will take now any metric space. And I will take a subset. Let's use A to denote that subset. And I want it to be non-empty. Because otherwise this is nonsense. So for each point, I will define first the distance from X to A. So the idea is something like here's my A, here's my point. I want to define what's the distance from X to A. And the idea is kind of, well, try going from your point to the set. Those are some ways of doing that. You could also maybe do something like this. That distance is going to be in principle larger than this one, and you want to take the smallest one. So what you're going to do is you're going to compute all distances from your point X to an element A. That's going to give you a set, and you're going to take the infimum of that set. And that's going to be the distance from X to A. So this is what I'm defining. So something to note. First, is this make sense? So this infimum exists because the set of all distances from X to A, where A lives in A, is a non-empty set because A is non-empty and it has an upper bound, namely 0. No, sorry, lower bound, because I'm computing infinite. That's a lower bound. And the second thing is what we're actually doing is, when I say for each X, define this, what we're actually doing is we're defining a function. So this defines a function. So this is something that we could have discussed just when we discussed metric spaces, not specific to compact spaces. But so this defines a function. Let's call it d of blank to A, going out of X to the reals, where little x will go to the distance from X to the set. So something that I want to mention, we're not going to prove this. This is a very interesting exercise. You should try to think about this. This distance function is continuous. And it will follow essentially from the triangle inequality. So yeah, I will not prove this. You should try to think about this exercise. Okay, why am I talking about this? Because this is what I want to do. And now we're going to define more generally what's a bounded space in a metric space or a bounded set. So again, we'll take a set, a subset maybe. Let's call it A, which I want to be non-empty. We're going to say that this subset is maybe, let's say, of a metric space. Space X, E is bounded. So this is what I'm defining. In case that there exists some positive m real, such that the possible distances that you get between two elements in A, so the distance from A to B, is going to be at most m whenever you have 2 points in A and B. So in other words, kind of the idea is your A looks something like this. Something like this, all right? And what we're trying to say is you cannot go too far away. There's something that's always going to bound the distances. So this is the definition of the bounded space. So first part and second part is in case F is bounded, we are going to define the diameter of A. So diameter as the following number. Diameter of A is going to be what you're probably guessing. So take all possible distances of two elements, and then, so all possible distances, distance from A to B, where A and B live in A, and now take the supremum of that set. So this is the diameter. Okay. And in this picture, the idea will be something like probably this distance. But it could be not so easy to compute it. So something to note: this diameter exists, or maybe let's say this makes sense. Taking this supremum makes sense. This sup exists because the set that this set over here, when we're taking supremum now, this set is not empty because A is not empty. Or we're assuming it has an upper. So it also has a smallest. Okay. And now we have a great theorem, and I will leave you with this theorem, and we'll discuss what it means next time. But I want you to think about this in advance. So, theorem with name, the Lebesgue lemma. And by the way, notice that everything depends on the metric that we have, not just the set. So let's take a metric space. Let's take a metric space, x, d. Now I want to talk about the topology coming from that metric. So let's take U to be an open covering of X. Remember, that means a collection of open sets for the metric topology that's going to cover X, whose union X. Then the claim here is that there exists a number. So there exists some positive number that should be called the Lebesgue number of the covering, such that for every so for every subset inside of X that has at most this diameter, A at most delta, we can always cook up some U in U that's in our covering that's going to contain A. And I said, oops, because I forgot something very extremely important, it's actually necessary for this theorem to be true, we need to assume X is compact. So I'm sorry, assume X is compact for the metric topology. And now this theorem follows. So what we're saying is whenever you take A with this diameter that we need to prove exists, so not too big of a set, then you can always include that in your open covering, whatever that open covering is. So the number will depend on the covering. This is the U that exists. And this is your A. Okay, so we'll prove this next time. Well, this is a very nice result about compact metric spaces. So yeah, that's it for today. I will see you on Monday.